When splicing 3 1/0 conductors running underground in 2-inch polyvinyl chloride conduit, several junction and splice box options are available. Here are some manufacturers and models to consider. Firstly, Siemens and IT offer the Lightning Protection 1200 series underground splice box model 1200-1009. Secondly, Arlington Industries provides the Model U500 26417 V3, which is a 6-gang grade polyvinyl chloride underground splice junction box. Thirdly, Crouse-Hinds offers the Model E600-2C-33, a 3-gang cast aluminum junction box with grounding provision. Fourthly, Eaton provides the Model LBK6B-33, a 6-gang polyvinyl chloride underground electrical junction box. Fifthly, Hoffman manufactures the Model A6000-33, a 3-gang outdoor NEMA 4.4x splice box. Regarding the use of Thomas & Betts long barrel copper connectors with lead-free solder instead of crimping, these connectors can indeed be used with lead-free solder as an alternative. However, it is crucial to follow the manufacturer's instructions meticulously and use the appropriate tools and materials. Soldering long barrel connectors offer several benefits. 1. It provides a strong and reliable connection. 2. It resists corrosion and loosening. 3. It can be used in areas where crimping is not practical or accessible. There are also considerations to keep in mind. Proper heat control is critical to avoid overheating and damaging the conductors. Ensure the solder flows evenly and completely around the barrel and connections. Allow the solder to cool and solidify before handling or installing the connection. Let's delve deeper into the selection of appropriate junction boxes. When choosing a junction box, several factors should be considered. First, the size of the conductors. Ensure that the junction box is appropriately sized for the number and size of conductors being spliced. A 1/0 conductor requires sufficient space for safe and effective splicing. Secondly, the environmental conditions. For underground applications, the junction box must be rated for direct burial and resistant to moisture, corrosion, and physical damage. NEMA ratings such as 4X indicate suitability for harsh environments. Thirdly, the material of the junction box. Polyvinyl chloride, cast aluminum, and stainless steel are common materials. Polyvinyl chloride is lightweight and corrosion resistant, while cast aluminum offers durability and grounding capabilities. Stainless steel provides excellent corrosion resistance for demanding environments. Fourthly, ease of installation. Consider the accessibility and ease of installation, especially in confined spaces. Features such as removable covers, pre-drilled mounting holes, and ample wiring space can simplify the installation process. Fifthly, compliance with electrical codes. Ensure that the junction box meets all applicable electrical codes and standards, such as those set by the National Electrical Code, or NEC. This includes proper grounding provisions and listing by a recognized testing laboratory like Underwriters Laboratories, or UL. Now let's discuss the process of soldering long barrel copper connectors with lead-free solder. Firstly, preparation. Thoroughly clean the conductors and the inside of the long barrel connector using a wire brush or emery cloth to remove any oxidation or contaminants. Apply a suitable flux to the conductors and the connector to promote solder flow and prevent oxidation during heating. Secondly, heating. Use a propane torch or a high-powered soldering iron to heat the connector evenly. Apply heat to the barrel of the connector, avoiding direct contact with the conductors to prevent overheating. Monitor the temperature of the connector using a temperature indicator or solder test to ensure it reaches the proper soldering temperature, typically around 400 to 450 degrees Fahrenheit for lead-free solder. Thirdly, soldering. Once the connector reaches the appropriate temperature, apply the lead-free solder to the joint. Ensure that the solder flows freely and evenly around the entire circumference of the barrel and into the connection points between the conductors and the connector. Continue heating until the solder melts completely and forms a smooth, shiny fillet around the joint. Fourthly, cooling. Allow the soldered connection to cool naturally without applying any external cooling methods. Avoid moving or handling the connection until the solder has solidified completely to prevent disturbing the joint and compromising its integrity. Fifthly, inspection. Carefully inspect the soldered connection to ensure that it is free from any defects such as voids, cracks, or incomplete solder coverage. Use a magnifying glass or visual inspection to verify the quality of the joint. If any defects are found, reheat the connection and apply additional solder as needed to achieve a sound and reliable joint. Sixthly, insulation. After the soldered connection has cooled and been inspected, apply a suitable insulation material to protect the joint from moisture, corrosion, and electrical contact. Use heat shrink tubing, electrical tape, or epoxy resin to insulate the connection, ensuring that the insulation extends beyond the soldered joint to provide adequate coverage. When considering the choice between crimping and soldering, there are several factors to consider. Crimping is a mechanical process that uses specialized tools to compress the connector onto the conductor, forming a secure electrical and mechanical connection. Soldering, on the other hand, is a thermal process that uses heat to melt solder and create a metallurgical bond between the connector and the conductor. Here's a comparison to help you decide. Firstly, reliability. Both crimping and soldering can provide reliable connections when performed correctly. However, crimping is generally considered to be more consistent and less prone to human error, as it relies on calibrated tools and standardized procedures. Soldering requires more skill and technique to ensure a proper connection, and it is more susceptible to variations in temperature, solder quality, and operator technique. Secondly, cost. Crimping tools and connectors can be more expensive than soldering equipment and materials, especially for larger conductor sizes. However, crimping can be more cost-effective in the long run, as it requires less time and labor to perform, and it reduces the risk of rework due to faulty connections. Soldering may be more economical for small-scale projects or repairs, but it can be more costly for large-scale installations due to the increased labor and material costs. Thirdly, ease of use. Crimping is generally easier to learn and perform than soldering, as it requires less skill and technique. Crimping tools are also more portable and convenient to use in the field, as they do not require a power source or open flame. Soldering requires more training and experience to master, and it can be more challenging to perform in confined spaces or adverse weather conditions. Fourthly, environmental factors. Crimping is generally more resistant to vibration, corrosion, and temperature changes than soldering. Crimped connections are also less likely to loosen or degrade over time, making them suitable for demanding applications such as automotive, aerospace, and industrial environments. Soldered connections can be more susceptible to corrosion and thermal stress, especially in harsh environments, and they may require additional protection such as conformal coatings or epoxy encapsulation. Fifthly, code compliance. Both crimping and soldering are recognized methods for making electrical connections under the National Electrical Code, or NEC, and other electrical standards. However, the NEC requires that all electrical connections be made in a workmanlike manner and that they be suitable for the intended application. It is important to follow the manufacturer's instructions and industry best practices when crimping or soldering electrical connections to ensure compliance with the NEC and other applicable standards. To summarize, selecting the right underground splice box and choosing the appropriate connection method, whether soldering or crimping, are crucial for ensuring the reliability and safety of electrical systems. By carefully considering the factors discussed and following the recommendations provided, electrical professionals can make informed decisions that result in durable and compliant installations. Let's now expand further on the considerations for soldering long barrel copper connectors, emphasizing best practices for heat control, solder flow, and cooling. Heat control is paramount when soldering to prevent damage to the conductors and ensure a reliable connection. Overheating can cause the insulation to melt or char, reducing its effectiveness and potentially creating a fire hazard. It can also weaken the copper conductors, making them more susceptible to breakage or corrosion. Conversely, insufficient heat can prevent the solder from flowing properly, resulting in a cold joint that is weak and unreliable. To achieve proper heat control, use a temperature-controlled soldering iron or torch and monitor the temperature of the connector with a temperature indicator or solder test. Apply heat evenly to the barrel of the connector, avoiding direct contact with the conductors. Keep the heat source moving to prevent localized overheating. The ideal soldering temperature for lead-free solder is typically between 400 and 450 degrees Fahrenheit. Solder flow is another critical aspect of soldering. The solder must flow freely and evenly around the entire circumference of the barrel and into the connection points between the conductors and the connector. This ensures that the solder wets the metal surfaces properly, creating a strong metallurgical bond. To promote solder flow, use a suitable flux that is compatible with the solder and the metals being joined. Apply the flux to the conductors and the connector before heating to remove any oxidation and prevent it from reforming during the soldering process. Use enough solder to fill the joint completely, but avoid using excessive solder, which can create a messy and unreliable connection. Feed the solder into the joint from the opposite side of the heat source to allow it to melt and flow into the connection. Cooling is just as important as heating and soldering. Allowing the soldered connection to cool naturally without applying any external cooling methods prevents thermal stress and ensures that the solder solidifies properly. Avoid moving or handling the connection until the solder has solidified completely to prevent disturbing the joint and compromising its integrity. Rapid cooling can cause the solder to crack or become brittle, reducing its strength and reliability. If necessary, use a fan to gently circulate air around the connection to dissipate heat, but avoid directing the fan directly at the connection. Let's now discuss the selection of appropriate tools and materials for soldering long barrel copper connectors. Firstly, the soldering iron or torch. Choose a soldering iron or torch that is appropriate for the size of the conductors and connectors being soldered. A high-powered soldering iron with a wide tip is suitable for soldering larger conductors, while a smaller soldering iron or torch is better for smaller conductors. Secondly, the solder. Use a lead-free solder that is specifically designed for electrical applications. Lead-free solder is environmentally friendly and meets regulatory requirements in many jurisdictions. Choose a solder with a suitable diameter for the size of the conductors being soldered. Thirdly, the flux. Use a flux that is compatible with the solder and the metals being joined. Rosin core solder contains flux internally, while paste flux is applied separately. Choose a flux that is non-corrosive and electrically non-conductive to prevent damage to the conductors and connectors. Fourthly, the cleaning supplies. Use a wire brush or emery cloth to clean the conductors and connectors before soldering. Use a solvent such as isopropyl alcohol to remove any residue or contaminants from the surfaces. Fifthly, the safety equipment. Wear safety glasses, gloves, and a respirator when soldering to protect yourself from fumes, heat, and molten solder. Work in a well-ventilated area to prevent the buildup of harmful fumes. In addition to these tools and materials, it is also important to have a suitable workspace and adequate lighting. Choose a work area that is clean, dry, and well lit. Use a soldering mat or other protective surface to prevent damage to the work area. With the right tools, materials, and techniques, soldering long barrel copper connectors can be a reliable and cost-effective method for making electrical connections. However, it is important to follow all safety precautions and industry best practices to ensure a safe and successful outcome. The choice of splice box depends largely on the specific installation environment and local electrical codes. For direct burial applications, boxes rated for underground use are essential to prevent water ingress and corrosion. These boxes often feature robust construction and sealing mechanisms. In contrast, for above-ground installations in damp or potentially corrosive environments, NEMA 4 or 4X rated boxes are recommended. These enclosures provide protection against splashing water, hose-directed water, and corrosive agents. The material of the box is another critical consideration. Polyvinyl chloride boxes are lightweight, non-conductive, and resistant to many chemicals, making them a popular choice for general applications. However, they may not be suitable for environments with extreme temperatures or high mechanical stress. Cast aluminum boxes offer excellent mechanical strength and are often used in industrial settings where durability is paramount. Stainless steel boxes provide superior corrosion resistance and are ideal for marine or highly corrosive environments. Finally, the size and configuration of the splice box must be adequate to accommodate the number and size of conductors being spliced, as well as any necessary grounding connection. The box should also provide sufficient space for safe and easy access to the connections for inspection and maintenance. Consulting local electrical codes and regulations is always recommended to ensure compliance and safety.